Hi everyone. Today the topic of my talk will be finding all positive rationals over which the generating function of the Fibonacci sequence gives integer values. Before I start talking about it, I'd like to give an anecdote on where we got this problem from. Basically, recently I was at a meeting with a group of professors and teachers at SUNY Westbury College. And we were there to discuss the possibility of organizing a high school math competition. Towards the end of that meeting, they gave me this problem. So here it is. This is not exactly what I'm going to talk about today, but so this was the first version, I guess. So let fx equal to this, which is essentially the generating function of the Fibonacci sequence. And then show that if x is a ratio of adjacent terms of Fibonacci sequence that is within the interval of convergence of f, then f of x is an integer. Yeah. I solved the problem before I left the campus, and then they asked me to prove the converse as well. And so the converse and the problem itself combined would be the topic of the talk today, which is essentially characterizing all positive rationals over which the Fibonacci generating function gives integer values. The talk will be divided into three parts. The first will be an introduction, and then afterwards we'll discuss two approaches to solving the problem, and then some extensions and an unsolved generalization of the problem. So here, problem statement, Fibonacci sequence is this, and then the generating function. And so we know that f of 0 is 1 because well, these are x to the positive powers, so these all vanish, and we're left with this term. So now we ask, are there any other rational numbers that are positive that would give an integer value of the generating function? And we can also actually characterize all x, and these x are in fact all positive because the negative numbers, none of them with the closed form satisfying this property here would actually be within the interval of convergence, which we'll discuss later. So now we're going to talk about the closed form of the generating function. Note that f of x is here, and then after we multiply the quantity by x squared plus x, we can actually get the coefficients to match up for the most part. So 2 here, 3, 5, etc. Everything matches up except for the first term, where we have 1 here and 0 for a constant term. So now we can subtract these two equations and obtain a closed form of f, which is here. And this closed form will help us solve the problem, but before that, just some basic properties. The interval of convergence of the closed form is negative 1 over phi, where phi is the golden ratio. And for positive rational numbers, x, where we can write it as a reduced fraction p over q. And then we can substitute into f and then get this value here, which is mostly what we will be working with. And so because the numerator and denominator are relatively prime, this means that when f is an integer, the denominator must be equal to 1. Well, we assume that x is positive, so f of x must be positive. And now we can use this to reduce the problem. We know that basically this condition also implies that p and q are relatively prime positive integers. So the problem becomes equivalent to finding all pairs p, q positive integers, such that this relation holds. And so from here on, we'll present two approaches to solving this equation. So the equation here is known as a Diophantine equation because we're only interested in integer solutions. And this Diophantine approximation approach is the approach cited by one of the professors who gave me this problem in his research paper that was based on this result. Diophantine approximation is basically approximating real numbers by rational numbers. And there's this thing called continued fractions, basically representation of a number as a nested sum of integer and reciprocal of another number. And then the formal definition is given here. Basically, everything is an integer except where A0 can be negative, but all the others are positive. And the convergents, they are truncated fractions in the continued fraction representation. So for example, the first convergence to x will be A0 plus 1 over A1. And then the second will be A0 plus 1 over A1 plus 1 over A2, and ignoring these. And each of these convergents yield an approximation to the number x. And when x is rational, this eventually terminates. And when x is irrational, the sequence AI goes on and on indefinitely. So here's an example, I guess, that will also be used later on, the result of it. So the golden ratio we can write as a continued fraction this way. So it's actually, basically we take 1 here because that's the largest integer that does not exceed the golden ratio. And then the remaining part we can write as this. We note that the golden ratio reappears in the denominator, so we can repeat the process to obtain this continued fraction expansion of the golden ratio. And the convergents are given by these, which are precisely ratio of adjacent terms of Fibonacci sequence. So now going to use a lemma here. That the lemma will not be proved in this presentation, but the proof can be found in many standard number theory textbooks. So it basically, essentially what it says is that whenever a rational number approximates an irrational number well enough, the well enough is basically determined by the size of its denominator. When the denominator is larger, you can get closer approximations. When this approximates well enough, then it must be one of the convergents of the irrational number. And in this case, from this relation here, we can solve for the rational number q over p. This turns out to be close to the golden ratio because when p is large, this term goes away. And we can actually check that difference is less than 1 over 2p squared for all p greater than or equal to 2. So q over p must all be convergents. And now, because q over p is greater than the golden ratio, note that the index must be even here and odd here. Otherwise, this ratio will be less than the golden ratio. So, and then for p equals 1, this edge case that's not covered above, we can check that q equal to 2. So this relation still holds. Any questions so far?
Yeah, I don't see why when it's odd, when you take like the reciprocal.
Oh, so basically these numbers, maybe it's easier to write here. So these numbers are 1 over 1, and then this is 2 over 1, and 3 over 2, and 5 over 3, and so on. So this number is equal to 1, that is 2, and this is 1.5, and this is 1.666, and then repeating. Basically, the golden ratio of phi is equal to 1.618, sorry, 66618 through 3 and so on. You can see that these fractions alternate between being below this golden ratio and then above. You can actually rigorously prove this, but it's just some calculations and not particularly insightful, but basically this is why. We only take these ones that are greater, the ones that are greater than the golden ratio here. Otherwise, 1 over this number would not be in the interval convergence. Up to this point, we have just found the answer to this question. It's basically just these ratios, and it can be verified pretty easily that these satisfy the problem condition. So next, I'll talk about my approach, which uses the theory of Pell equations. I found this solution on my own before. before, they showed me their paper which had this approach contained. And it goes like this. So first, what I did differently from that previous solution was I did not solve for Q or P, but I just solved for Q instead. And this gives another observation, which is basically that this is an integer if and only if this number is the square of another positive integer. And so we can rewrite this condition as follows. Basically, Q is a positive integer if and only if there exists R positive integer such that this holds. So what we have here, this relation, R, P are both positive integers. This is, in fact, a generalized Pell equation because the definition of a Pell equation is basically this x squared minus dy squared equal to plus or minus 1, and where d is a non-square positive integer. So the idea to solving these types of equations is to treat the quantity here as the norm of this number here in Q and D, the number field generated by a radical D. So the solutions are in a sense multiplicative. That is, we can multiply two solutions together somehow to obtain another one. The solution set is closed under multiplication. So in here, we have basically two cases. One case where both R and P are even, and we'll obtain a Pell equation here because this term is 1 now. And then when R and P are both not divisible by 2, these must be relatively prime, because if they're both divisible by, say, an odd prime, then odd prime divides 4. That is not possible. So in this case, we have a generalized Pell equation. And the method we're going to present here can deal with both cases, as we'll see in a bit. So the minimal solution, I guess I'll define this notion to just for ease of explanation here. So in here it's defined as the solution that minimizes the absolute value of y, but any sort of minimality characterization works here, such as absolute value of x or absolute value of x plus absolute value of y. Doesn't really matter. But you just have to basically be invariant when we switch x and y, when we switch the signs of x and y, because x satisfies this if and only if negative x does as well. So, and similar for y. We note that the minimal solution is unique up to the sign of x and y. And the minimal solution does not necessarily exist here, but it can be proved that when k equals to 1, this necessarily exists, and for k equal to 4, which is our case, it's really just 1 times 2 squared. So we can take a solution to the case where k equals to 1 and then multiply it by 2 to obtain another solution where, so this equation is always solvable. And so now, the minimal solutions we can actually check back end when d equals to 5 here. That the minimal solutions are 9, 4, and then changes of sign. And then for this later one, it's 3 and 1. Because, well, we can check that, for example, the first one, when y equals to 1, 2, 3, these don't work. Then for this, there is either y is 0, in which case we just have x equal to 2, but then that has y equal to 0. And x, y are not relatively prime. So these are the minimal solutions that we'll use later on. And so now, if we write x plus y radical 5 equals to the product of some other numbers of this kind, and then we can take the norms on both sides, which essentially tells us that each number of this form is also a product of some other numbers of this form. It doesn't really matter how many numbers there are in this product, and but because the norm is multiplicative, this always holds. And we can denote the norms of each of these numbers by the number Ri, and then the product of Ri over Ri is 4, which means that for each of whenever we can write it this way, most of the Ri have absolute value that is 1, all except one of them. and there's only one of these Ri with norm 4. And that is because, one of the Ri with absolute value 4. And that is because, well, Ri cannot equal to 2, because, whenever we have these being the same parity, this quantity will always be divisible by 4. But when there are different parities, then 2 does not divide this because it's odd. So we can just, also that, we can just denote the number with norm, absolute value of norm 4 be x0 plus radical 5 y0. And we note that because 2 plus rad 5 has norm -1, so whenever we have something with norm -4, we can just multiply it by this quantity and then also multiply the result by 2 minus -5. And the 2 minus -5 goes to becomes one of the xi plus rad 5 yi. And in that case, we can still have this holding. So we can just, without loss of generality, we'll assume that the xi plus rad 5 yi with norm 4, like 4 -4, actually has norm 4 for convenience. Any questions? Okay. So now we know that for any positive xy with yes.
So what are xi and yi?
So I give a example here. So the xi and y, for example, given just any number x plus rad 5y, this number is equal to, it's really just basically we were writing this into a product of some other elements that are in this number field here. So x plus radical 5y, this quantity itself, there are in fact infinitely many such representations, because we can just rewrite it as this. For example, I'll use that because in this case 9, 4 is a unit. We can do 9 plus 4 radical 5, and then 9 minus 4 radical 5. Oh, can you see? Oh, sorry. So this is equal to, each time we multiply it by a unit, it still holds, the value doesn't change. However, we obtain more terms in the product. So now this term becomes 9x plus 1ey, and then plus 13 9y plus 4x radical 5. And then this whole thing times 9 minus 4 radical 5. So that's, and then in this case, we can take this to be x0 and then plus y0 rad 5, and then here is x1 plus y1 radical 5. So you can, in fact, get infinitely representations this way. And in this case, we're not really interested in what exactly the xi and yi are. It's just, as you'll see in a bit, it just tells us that for any such representation, exactly one of them has norm 4, and the others has norm 1. So now, for any positive xy with the norm being 4, under most circumstances, we can multiply it by 9 -4. Recall that this is one of the units. But here we assume that xy are both positive, so we're choosing this one to reduce the absolute value of y. So if y is negative, then we can flip its sign and we get a positive xy that has a lower absolute value of y. And basically the idea is to just repeat this process until, well, we said under most circumstances, we'll repeat the process until this no longer holds. There are some specific cases where we cannot reduce the absolute value of y further. And in that case, we'll end up with the minimal solution to the Pell equation, the generalized Pell equation, x squared minus 5y squared equals to 4, and that's 3, 1 here. That's the minimal solution to the generalized Pell equation. And then this one is also another solution. I did not include the cases where x equal to -3 because we're only interested in positive values of x. So now otherwise if we never after we reduce this, after we repeatedly multiply this by -4, which can be thought of being the same as dividing this xy by 9/4. Recall that it's a unit. So if we never reach one of these forms, then we actually have y being 0. In that case, that's the end where we cannot reduce the absolute value of y further when y is 0. And then when y is 0, we can solve for x to obtain x equal to 2. So we get xy equal to 2 times 9/4 to the nth power, because each time we have reduced this by this quantity. And then otherwise, these are the solutions aforementioned. And in summary, we get these 3 families of solutions. So, any questions so far? Or about the previous slides, I guess.
So when you have that there squares, right? The thing under square root. Still, how do you know that it's even, like the sum is going to be even? So when you divide it by 2, you're going to get integers.
Oh, that. So you mean like in the quadratic formula part? Basically, because the equation q squared minus pq minus p squared minus 1 equals to 0. So when we treat this as polynomial in Q, this will always basically this will because it's an integer coefficient polynomial. All the roots of the polynomial must always be algebraic integers. So any algebraic integer that is rational must be an integer. And so as long as it's rational, then we know we're good. So basically, any other questions? So after we get these families of R and P, we can solve for P here to obtain basically 3 sequences of P. These each would satisfy recurrence relation of order 2, and then well, we can actually check that the 3 solutions, 3 families of solutions combined, they would give the Fibonacci sequence, but only the odd index terms, which is exactly what we wanted. So I found this result kind of surprising because just by those formulas, it doesn't look like they are Fibonacci sequence. But we can actually verify that these satisfy the recurrence relation that is also satisfied by f6k plus 1, f6k plus 3, and f6k plus 5 here. So that's the Pn plus, Pn minus, and Pn naught. The signs here chosen are because of the signs are chosen just for convenience here. We have 1 in y, and so that's a plus, and then -1, so minus here, and then because it's 0 here, so I just negative P naught. And yeah, so that's just another approach that gives some different insight to the previous one. And we notice that each family of solutions to the Pell equation corresponds to a third of the Fibonacci sequence, so that is has odd index, so to say. And with a bit more analysis, the case of the problem with negative rationals can also be done in the same methods. But the answer turns out to be f2k plus 1 divided by f2k, and the negative of this. And then, so each of these terms has absolute value that is at least 1. So these are not within the interval of convergence of f. And so what we have found are in fact the only rationals that makes fx an integer. And so now the unsolved convergent general problem is here. Before I state it, it will be convenient to define the notion of a homogeneous linear recurrence relation. It's basically a recurrence relation of this form. A sequence defined by such relations has k degrees of freedom. So k is the degree of the linear homogeneous recurrence relation. Because each such sequence is determined by the first k terms of AI. So for example, the Fibonacci sequence is defined by a homogeneous linear recurrence relation of degree 2. And the general problem asks for linear homogeneous recurrence relations, AI, what are the rational values of x that would give the integer values of the generating function. So the professor, one of the professors that gave me this problem, he co-authored a paper that shows that the answer is still ratio of adjacent terms basically for the linear recurrence relations of degree 2 with initial terms 0 and 1. And also that the coefficients in the recurrence relation here must be of this form. That is C2 must divide C1. And then for some AD positive integers here. And yeah, that's it. So, thanks.
Any other questions?
So, why did you consider numbers of the form a plus b squared
Why did I consider numbers of which form? Sorry.
a plus b squared pi?
Oh, this.
Yeah.
Oh, because consider these because we are treating the quantities a squared minus 5b squared as the norm of this number here. So that because this is more like an intuition, we don't really need this, but it just kind of tells why we can sort of multiply the solutions together, and just so that the reduction part that's here would make more sense intuitively, I guess. Where it is? Yes, this. So essentially, each time we're dividing x plus rad 5y by this quantity 9 plus 4 rad 5. That's what we are doing. It's reducing the size of this number. Then because this is a unit, so after we divide x plus rad 5y by this number, it still stays in z rad 5, and so the numbers that are in so numbers here, they still correspond to an integer solution to x squared minus 5y squared equals to 4. Any other questions? Okay, thanks.
Thank you.